Okay, let us start our lesson today. As we wait, I think others will find us on the way going. Want to look at prime field extensions. We've been looking at fields, and so it's good time to look at extensions. So what do we mean by this? So you're given a field, and then out of this, you want to come up with a bigger field. That is what we call an extension of the previous field. So field extensions are very important concepts in field theory, and of course, important in cryptography. So if you are given a field, what we'll be doing is that be creating bigger or larger fields out of the fields given to us. So if you're given F2, that this is a field mode 2, you can create other bigger fields. You can create F4 out of this, and we shall call it F22. This is how we shall be abbreviating it. You can also form F23, can form F24, and so on. So you can see that like this field has only 2 elements. This has 2 elements, 0 and 1. But this one will have 4 elements. This will have 8 elements, 2 raised to 3. This will have 16 elements, and so on. So out of this field, we can create larger fields. So this we shall call it the base field. This is the one that is given to us. Out of this, we create other fields, and those other fields, we shall call them extensions or field extensions. So that is, of course, what we'll be doing. So you're given a base field, and out of that, you create extensions, and so those we call them the field extensions. Like now, in this case, this 3 becomes the degree of this field. So this field will be of degree 3, and this one will be of degree 4, and so on. Where are these powers coming from? These ones are coming from irreducible polynomials, and we'll be seeing how irreducible polynomials are coming in. So if the irreducible polynomial, if you considering an irreducible polynomial of degree 3, then what you can create is 2, 3. So this 3 is the degree of the polynomial. And then it becomes now the degree of this field extension. The polynomial under consideration should be irreducible. Should be an irreducible polynomial. We shall see how that happens. Now, so what follows are just terminologies, and after that, then we move straight away to constructing field extensions. Now, supposing this is the base field, and out of this base field, you created an extension. So this base field is therefore a subfield of the extension. Now, so we'll denote the extension this way. This how we denote it sometimes. We denote it this way to mean this is an extension, and you're creating it from the base field. The base field is F. Now, if there's no contradiction, then we just write K. If there's no contradiction, but to avoid contradictions, then we will write that to mean a field extension where the base is F and K is the larger field created out of F. Now, I had mentioned about the degree of the extension, and that degree of the extension shall be denoted this way. So this is how we denote the degree of the extension. So when you see this, it means the degree of the extension. So that's what it then means. So if the degree of this extension is finite, then the extension shall be known to be a finite extension. If the degree is finite, that means if the degree is a number you can count, if the degree is, let me say, 2, 3, and so on, then we shall say that is a finite extension. But the degree, if the degree is not finite, then it will be infinite. Now, again, these are just terminologies that you may want also to interact with and understand what they mean. We've already said that where there's no contradiction, where there is contradiction, then we shall denote our extension this way. But if there's no contradiction, and then you will just write K, and we will understand you're talking about an extension of where F is the base. Now, supposing inside this extension, the extension will have elements, and we said, for instance, if the extension is F2, 3, then it would be having 8 elements. Supposing we have an element alpha, part of this, when do we say that alpha is algebraic? Alpha is an element of this extension. So when do we say that alpha is algebraic over F? So we say that alpha is an algebraic over F if we can determine that if given a polynomial, of course, we talked about the irreducible polynomial, and that polynomial is should be a member of this, field. Then if alpha be called an algebraic over F if alpha is a solution. If alpha is a solution to this polynomial, if alpha is a solution, that means when you replace alpha where there is x, and then you get 0. So supposing we are talking about F2, and then we have a polynomial like x2 plus 1. Of course, this polynomial is part of this field, is a member of this field. Now, so we say, therefore, that alpha is an algebraic over F if you can determine one polynomial inside this. If you can determine one polynomial inside this, such that alpha would be a solution to that polynomial. Remember, alpha is an element of the extension. So you're saying that if you can determine, and remember that this was the base. This was the base of this extension. So you're saying that alpha, which is a member of this extension, be called algebraic if you can determine one polynomial inside here, such that alpha is a solution to that polynomial. Now, in some cases, you'll find that we don't get such polynomials, that you can search for this polynomial and you will not find it. That alpha will not be a solution to any polynomial. That alpha member of this, okay, we will have some members of this that will be solutions to some polynomials, but we will also have some members of this extension that will not be solutions to any polynomial. In that case, then we say that alpha is transcendental, over F. That means you have this element and you try the other polynomial in this field, and you find that this element is not a solution to any of the polynomials. Then we shall call that element transcendental. So these are just some terminologies that will be important for us also to note. Then now let's go straight to constructing extensions. This is also just a terminology. I've said a finite field extension of this. So this is our base field. So a finite field extension of this will be a field that contains this. That's what we've already said. We've already said that if K is a finite, an extension, then this K should contain the base field. That's what we've said. That's what this statement is just, this statement implies. Is what this statement implies. That every extension would contain the base field. And again, we've said that if this is the base field and you're creating this extension out of this, we've said that the elements of this will be 2 raised to 3, which is 8, for instance. And that's what I've said, that this finite field will contain the base field and also has a finite number of elements. Would have a finite number of elements. For instance, this one has 8 elements. You might have also 2 raised to 16, and we know how many elements are these. Now, so these fields, the field extension fields, these finite field extensions, in fact, these are what we call the Galois. You'll find books calling them Galois fields. And this is how we denote them. These are we denote them. In this case, our number here is prime. Is prime. So we cannot have something like 8 here. Raised to 8 is not prime. So the number, this number must also always be prime, but this can be any number. It can be any positive number. So this just explain what we've already explained. We've already explained that it will have 2 raised to 3 elements, for instance, but this one will have p raised to n elements. Now let's go straight to how do we construct a field extension. And we've been given this base field. And we've been asked to construct an extension, this extension. So it means, of course, we'll be using a polynomial of degree 2, irreducible polynomial of degree 2. And this is where the degree is coming from, this power. It's telling me the degree of the polynomial that I'll be using. But of course, I already said earlier on that this polynomial would be very important to us, especially in multiplication. But when it comes to just constructing, we don't require this polynomial. We require it in the multiplication of the elements of this field extension. But something we need to always remember is that the elements of this field extension are polynomials, and they are of the form a plus b alpha. The elements of field extension, this field extension, are polynomials of this form, where a and b are elements of the base field. Elements of the base field. In our case, the base field is this, and the elements are 0 and 1. So we want to construct a field extension, F22. We have to remember that the elements of this will be polynomials, and these polynomials will be of this form, a plus b alpha, where a and b are elements of the base field. So now how do we construct? Again, we consider all scenarios, all possibilities. So what I mean by that, having known that the elements of this extension will be of this form, where A and B are members of the base field, and in this case, 0 and 1. So we try all possibilities. For instance, A could be 0, and B could also be 0. So if both A and B are 0, what does the element become? This is the element. What does it become? So A is 0 and B is 0. So the element then becomes 0 also. Because it will be 0 plus 0 alpha, and that is 0. So we consider all possibilities. The other possibility is that A could be 0 and B could be 1. That's another possibility. So if that is the case, what does this element become? So A is 0 and B is 1. So this would be 0 plus 1 alpha. 0 plus 1 alpha, and this gives us alpha. So this is the second element we've obtained. This is another element of this field extension, and we're getting elements of this field extension. The other possibility, we've exhausted all scenarios when A is 0. When A is 0, these are the possibilities that B could be 0, or A could be 0 and B could also be 1. B could be 1. So the other scenario is when A is 1, B has a possibility of being a 0 at that point. And when A is 1, B also has a possibility of being 1. Just choosing these elements from here. Now let's look at this scenario. When A is 1 and B is 0. A is 1, yeah, just now back to the elements. A is 1 and B is 0, so what you get is 1. And then this other possibility, A is 1 and B is 1, what you get is 1 plus alpha. So now the elements of the field extension, therefore, are what we've just obtained, 0. I can say 1, then alpha, then 1 plus alpha. These are the elements of this field extension. You can see that we've obtained 4 elements. That's what we said. That's what we said, that if you have p raised to 2, then we'll be having, in this case, our prime number is 2, then raised to 2, you have 4 elements. And what is important is how we obtain those elements. We've now obtained those elements of the field extension. Now, it's important to note that a field extension is also a field. A field extension is a field. That means it fulfills all the properties of a field. So you can add the elements of this field extension, and you see closure, associativity, commutativity, and you can also multiply and see the same properties. So that's what I was doing at this point. I was just trying to come up with the elements of the field extension, and we've just done that. Now, after this, I've said a field extension is a field. So for us to show that it's a field, we want to show that you can add elements of the field extension and get an element of the field extension. So let's do addition. The first element we got was 0, and then we had 1, we had alpha, then we had 1 plus alpha. Again, we have 0, 1, alpha, then 1 plus alpha. Now just add 0 and 0 will just be 0, 0 plus that will be 1, 0 plus that will be that, and 0 plus this 1 plus alpha. Add 0, get just 1 plus alpha. And then 1 add with this, add 1 to 0 will be 1, 1 to 1 will be 2, but we are doing it F mod 2. This is our base. Our base is mod 2. So that means when we get to 2 or anything less, we must divide by 2 and then write the remainder. So the remainder in this case is 0. The remainder in this case is 0. And then 1 plus alpha will be giving us 1 plus alpha. Then 1 plus this, so what we have is 1 plus alpha. This is 1 plus this is 1 plus alpha. So this gives us 2 plus alpha, but 2 mod 2. 2 goes here, the remainder is 0 plus alpha. So this gives us alpha. Now, when you're doing this, you know that every time you're going to add, you must get an element of this set. And the elements of the set are 0, 1, alpha, 1 plus alpha. We had already obtained 1, 0, 1 plus alpha. What was left was just alpha. We just have even put, but we wanted to verify. Because we knew we were to get, each element has to appear once. Now let's add alpha to each of them. This will be alpha. Then alpha plus this will be 1 plus alpha. And then alpha plus this will be 2 alpha. 2 alpha. But we are doing it mod 2. Mod 2. So 2 goes here, and the remainder is 0. And then alpha, of course, we know what is left. What is left is 1. So we can just fill. But let's just add again. It will be 1 alpha plus 1 plus alpha. So this gives you 2 alpha plus 1. But the 2 alpha goes to 0, so you're left with 1. Now let's add this element with that. That gives you 1 plus alpha. And then this element plus that gives you alpha. And then this element plus that gives you 1. Then this element plus that gives you 0. Let's just see if it gives us 0. We have 1 plus alpha, then plus 1 plus alpha. So this is 2 plus 2 alpha. And we are doing this mod 2. So we are dividing each of them by 2 and writing the remainder, which is 0. So we've shown one property that it's supposed to show for us to say it's a field. So of course we've shown not one property, but several properties. We've shown closure. That every time you add any 2 elements, you get another element of this set. We've shown that. We've shown several properties. So in fact, we can show that we've shown that every element has an inverse. Under addition, we've shown that every element has an inverse because in the under addition, the inverse of A is B if these 2 give us 0. So that therefore means I can see that the inverse of 0 is 0. 0 plus 0 is giving me 0. So the inverse of 0 is 0. I can see that the inverse of 1 is 1 because the sum of 1 and 1 gave me the identity. 1 plus 1 gave me the identity. So the inverse of 1 is 1. And addition. I can also see the inverse of alpha as alpha. The inverse of alpha is alpha because I can see that alpha plus alpha has given me the identity element. I can also see the inverse of 1 plus alpha as 1 plus alpha. So in fact, in this case, every element was its own inverse. Because I can see 1 plus alpha plus 1 plus alpha giving me the identity element. So, and of course, we've shown that 0 is the identity, because when I added 0 to each of the elements, I got the element 0 plus 0 gave me 0, 0 plus 1 gave me 1, 0 plus alpha gave me alpha, 0 plus 1 plus alpha gave me 1 plus alpha. That means 0 has no impact on any of the elements, so it's the identity element. So again, we've shown that. Now, what about multiplication? Let's just try multiplication very fast. Let me just erase this, or I can leave it. Somebody might have a question later. 1 plus alpha, alpha, 1, 0. Multiplication. 0, 1, alpha, 1 plus alpha. Now, this is where I said, for you to multiply, there are elements we would do straight away multiplication, but the elements that will require an irreducible polynomial. So let's see, when we reach there, and then we will look for an irreducible polynomial. 0 times each of these elements will give me 0. 1 times each of these elements will give me the element. So up to there, we are okay. Now let's multiply by alpha. Alpha by 0 is 0. Then alpha by 1 is alpha. Alpha by alpha is alpha squared. But you realize that alpha square is not an element of this set. Elements of this set are here. There are 0, 1, alpha, and 1 plus alpha. So this is not an element of this set. So you must convert it to be an element of this set. So that is why you go back now, choose an irreducible polynomial. I had already chosen this as an irreducible polynomial. And of course, you can choose any other. There's no method for choosing a polynomial. You only need to verify that this polynomial, the degree is what you've been asked. You were asked to come up with f of 2. So the degree of the polynomial must be this 2. So that is what I did. You can see my polynomial is of degree 2. And the other thing you need to verify is that the polynomial is irreducible in the field. It must be reducible in f of 2. So the polynomial that I've chosen is irreducible because you can try the elements of f2. The elements of f2 are 0, 1. You can try and you discover that none of them is a solution. For instance, when you try 0, and then you will have 0 squared plus 0, that gives you 1. So 0 is not a solution to this polynomial. You also try 1. When you try 1, you get 1 squared plus 1, that gives you 2. Then plus 1, that gives you 3. But you are doing it mod 2. Mod 2, so that gives you again 1. So that means 1 is not a solution to this polynomial. So the polynomial, therefore, is irreducible. It's not the only one that is irreducible. People also have even used f of x. I think this is also irreducible. But the thing is, no, this one is not. This one is not irreducible. This one is not, because when you try 0, f of 0 will give you 1. What about f of 1? F of 1 will give you 2, which is 0. So this is not irreducible. This is not irreducible. And in fact, but you can make it irreducible, for instance. Let's see. You can even add something else. When you find that this is not irreducible, you can continue, you can add an x. That's what I did here. I added an x and then added a 1. What about adding an x alone? Adding an x alone does not, it remains reducible. because when x is 0, then this one becomes 0, 0. So it will be reducible. So then I said, what about if I subtract 1? Can even subtract 1 from it. What happens? And x is 0, this will be 0, 0, minus 1, which is just 1, minus 1, which is just 1. Of course, this is just the same as this. Just the same as this. I just converted this one mod 2. Mod 2 to be positive 1. So these polynomials, there's no formula. You just have to check, is it irreducible? The way I'm checking here, I just began with the x squared plus 1. You can even begin with just x squared. And you realize that when it's x squared, then when x is 0, it will be 0 by solution. So it will mean that this is not irreducible. Then you try and add something. And you discover it's again, you add something, you add an x and so on. Of course, when you do that, you always find a polynomial that is irreducible. You are trying this, you're trying that. And before you go far, you will have obtained 1. So there's no formula that a polynomial must be. The only 2 conditions, that the degree of the polynomial should be the same as the one given for the extension, and that the polynomial must be irreducible. Now, so we proceed with our multiplication. So we've now chosen the polynomial. We've chosen this polynomial. And we arrived here and found that alpha times alpha was alpha squared. So let's imagine, therefore, that alpha is a solution to this polynomial. Let's imagine. So if alpha is a solution to this polynomial, then we would find that alpha squared plus alpha plus 1 is supposed to give us 0. If alpha were to be a solution to this. So what then is alpha squared? Alpha squared, therefore, is minus alpha minus 1. So that means instead of alpha squared, you can write this. But we just want it to be positive. We are doing it mod 2. Mod 2. So mod 2, this is negative 1 alpha, and this is negative 1. So this negative 1 mod 2, just add it to it, becomes positive 1. And this one again added to it becomes positive 1. So that what we then get is alpha plus 1. So instead of alpha squared, therefore, we have alpha plus 1, or 1 plus alpha. Now let's multiply now alpha and this. So it's alpha and 1 plus alpha. And when you do this, you get alpha plus alpha square. But we already know what alpha square is. Is alpha plus 1. So instead of this, what we have is alpha plus 1. Because this is our alpha square. So this gives you 2 alpha plus 1. But we know what 2 goes to mod 2. It goes to 0. So we're left with 1. This was 0. So in fact, we will have known that we were going to get 1 because we had already obtained 0. We had obtained alpha, we had obtained 1 plus alpha. The only remaining element was 1. Now, let's now multiply this 1 plus alpha by each of the elements. This gives us 0. 1 plus alpha times that gives us 1 plus alpha. 1 plus alpha times this is the same as alpha times 1 times plus alpha. They're commutative. The element remaining here is alpha. That is the element remaining. Otherwise, you would have obtained it. Let's just obtain it. 1 plus alpha times 1 plus alpha. This will be 1. Then 1 times alpha gives us alpha. This is 1. Alpha times 1 is alpha. Then alpha times alpha is alpha square. Of course, we know what alpha square is. And we also know that this one is alpha plus alpha is 0. Alpha plus alpha is 0. So what we now have is 1 plus alpha square. But this is same as 1 plus alpha plus 1, which is alpha. Because 1 plus 1 is 0. So you get alpha. So we've done multiplication again. When you look at this, under multiplication, the identity element is 1. So the inverse of an element under multiplication is B if their product is identity 1. So the inverse of B is A if this product is 1. So what that tells us, that the inverse of 1 is 1, because you can see that their product gives us the identity. It also tells us that the inverse of alpha is 1 plus alpha, because that product gives us the identity. And you can also see that the inverse of 1 plus alpha is alpha, because this product gives us the identity. So you have seen commutativity and so on. So that's how we've generated elements of the extension F22. After that, we've seen how to add those elements and how to multiply the elements of the extension. So again, we can take another example and just emphasize how to come up with a polynomial that is irreducible and how to add the elements of the extension and how to multiply them again. Okay. Now, so let's look at this other example. In this second example, we've been given the base field F3, and we are required to get F32. So that means we'll be choosing a polynomial of degree 2 at some point if we are to multiply the elements of this field. An irreducible polynomial of degree 2. But before that, let us start by, first of all, generating the elements of this extension. There will be 9 elements from what we see here. 3 raised to 2. There will be 9 elements. And we know the format. We know that the elements of the extension would be of the form A plus B alpha. And that these elements will be 9 of them. So where A and B are these elements of the base field. A and B are coming from these elements. So let's now proceed and obtain the elements of the extension. So the first possibility, let's consider when A is 0 and B is 0. And so what does this element become? When A is 0 and B is 0, we obtain an element 0. That's the first element you obtained. The other possibility, A could be 0 and B could be 1. We're just choosing elements from here and considering all possibilities. So if A is 0 and B is 1, we're substituting here. This is 0 and this is 1. So it will be 0 plus alpha, which is alpha. So we obtain alpha. The other possibility, A could be 0 and B could be 2. So again, replacing 0 and 2, you have 2 alpha as the other element of the extension. We've exhausted all possibilities if A were to be 0. If A were to be 0, these are the 3 possibilities. So we also have the option of A being 1 and B could be 0. A could also be 1 and B could be 1. And then A could be 1 and B be 2. These are the other 3 possibilities. Now, so let's consider this possibility. If A is 1 and B is 0, we just come back here. A is 1 and B is 0, we get the element 1. Come back and consider the other possibility, A1 and B1. We have 1 plus alpha. 1 plus alpha is the other element. And then we have 1 plus 2 alpha. 1 plus 2 alpha. So generating these elements is very easy. Coming up with elements of the extension. Now, so we've considered 2 possibilities, A0 and A1. Let's now consider the last possibility. When A is 2, B could be 0. Or A is 2 and B could be 1. Or A is 2 and B is 2. So if A is 2 and B is 0, then you obtain the element 2. Just going back here and substituting A and B. If A is 2 and B is 1, then you have the element 2 plus alpha. And if A is 2 and B is 2, then you have the element 2 plus 2 alpha. 2 plus 2 alpha. This is the element. This must be 9 elements. 1, 2, 3, 4, 5, 6, 7, 8, and then 9 elements. We've obtained the 9 elements of the extension. This is how you obtain those elements of the extension. So now again, as usual, we want to show that this extension, of course, is a field. So to do that, we want to see how to add the elements of this extension and how to multiply those elements. Very easy, just like that. So let's go to addition. And of course, when it comes to multiplication, we'll need to, again, define our irreducible polynomial. And as I said, if you have several people, different people, they'll be coming up with a different polynomials. They'll be coming up with a different polynomials. But now, when you create a multiplication table, that multiplication table will be the same. That multiplication table will be the same. Although the polynomials will be different, but we expect that the elements will be identical because the elements that we've generated are the same. So just using that polynomial to write where there's an element coming out that is not directly one of the elements, you bring in the polynomial and you get another element of the field. You get another element of that field. So let's do addition, then first, then we'll come back to the polynomial just to see how to come up with one. This we've already done. I was just getting the elements of this field, this extension, and then I said these are the elements of the extension. Now let's go straight to addition table. These are our elements. I've put them in this row and this column. We just want to add these elements and create an addition table. I'll do just 2 or 3 examples and then we proceed. 0 with the n of these elements, you get the element. 0 and 0, 0, 0 and 1 with that. 0 and 1 plus alpha, 1 plus alpha, and so on. It's very easy doing that. Let's add 1 to n of these elements. 1 plus 0 will be 1. Remember, our field is base 3. Our base field is mod 3. 1 plus 1 will be 2. 1 plus 2 will be 3. And we are doing it mod 3 so that it reduces to 0. 3 divided by 3, the remainder is 0. 1 plus alpha will be 1 plus alpha. 1 plus 1 plus 1 plus this to be 2 plus alpha. Then this 1 plus this will be 3 plus alpha. But remember, this 3, you reduce it and you get 0. So this is supposed to be alpha, not x. It's supposed to be alpha. This was a mistake when I was typing. Now, so what about 1 plus 2 alpha? That gives you 1 plus 2 alpha. What about 1 plus this? So this would be 2 plus 2 alpha. 2 plus 2 alpha. Then 1 plus this. This would be 3. Mod 3, that gives us 0 plus 2 alpha, which is 2 alpha. So it's very easy adding. Let's add this to each of the elements. So to add it to 0, you get the element. Add this to 1, you get 2 plus alpha. Add this to 2. This 2 plus this 1 gives you 3. Then that is 3 plus alpha. 3 plus alpha. But 3 goes to 0, left with the alpha. Then this plus this alpha gives you 1 plus 2 alpha. Then 1 plus alpha plus this. I hope you are following. 1 plus alpha plus this gives you 2 plus 2 alpha. Then this 1 plus alpha added to this. 1 plus 2 gives you 3. Mod 3, that will be 0. And alpha plus alpha gives you 2 alpha. And so on. And so on. Let's see. This is 1 plus alpha added to 2 alpha. That gives you 1 plus 3 alpha. But this goes to 0. So you left with the 1. Okay, 1 plus alpha added to 1 plus 2 alpha. 1 plus alpha added to 1 plus 2 alpha. So 1 plus 1 will be 2. Then alpha plus 2 alpha will be 3 alpha, but this goes to 0, which then is 2. And then lastly, 1 plus alpha added to 2 plus 2 alpha. This gives you 3 plus 3 alpha, and each of them gives you 0. Because you are doing it mod 3. And you can see that every time you are doing that, getting elements of the set. Nothing is coming outside. So this set is therefore closed, as we always say. It's always closed. Every time you add any 2 elements of this set, get another element of the set. So we say, therefore, it's a closed set. Now, again, you can see that every element has an inverse under addition. Consider every element as an inverse. Under addition, we already said that under addition, the inverse of A is B. If the sum of A and B gives you the additive identity element 0. If A plus B gives you 0, then we say that A is the inverse of B, or B is the inverse of A, if that is the case. So very fast, we can identify that the inverse of A, therefore, is 2. Because A plus 2 gives you the identity 0. You can easily see that the inverse of alpha is 2 alpha because their sum is identity element. The inverse of 1 plus alpha, what is it? I'm just checking, is 2 plus 2 alpha because their sum gives the identity element. The inverse of 2 plus alpha, 2 plus alpha, the inverse is 1 plus 2 alpha because their sum is the identity element 0. So that is how you tell the inverse of an element and so on in this kind of question, because then you have to have that table. You have to have the table for you to tell what is the inverse. Now let's look at multiplication. How do we multiply? Now for us to multiply, let's identify a polynomial that is irreducible mod 3. Okay, so mod 3, of course, when it's doing mod 3, we know the elements are 0, 1, 2. So for a polynomial to be irreducible mod 3, it means none of these elements here should be a factor of this polynomial. None of these elements should be a factor of this polynomial. So let's choose, we can begin with x cubed. X cubed, no, not x cubed. Am I even writing the cube? Now, so we'd been given this. So the degree of the polynomial should be 2. The highest power of the polynomial should be 2 from that. So the thing I can just try is x squared. X squared is not irreducible because when you substitute x with 0, you get 0. So x squared is reducible. Let me add 1 to it. Can just add 1 and see. Can even add 2, there's no problem. Let's add 1. If you add 1, then this will be 0 plus 1. I'm trying f of 0. F of 0 will be 1. What about f of 1? 2. What about f of 2? F of 2 will be 2 square, which is 4, plus 1, which is 5, mod 3, which is 2. So none of this is a solution, and therefore this polynomial here, f of x, is irreducible. One will have come up with another polynomial. What about if you try and x squared plus 2? This is not irreducible. This is not irreducible because let's try x to be 1. So if x is 1, you can see that what you come up with will be 1 plus 2, which is 0. So this is not irreducible. So this one is not fit to be used here. What about if you try x squared plus x? This again is not irreducible because of course you can see this can be factorized. This is reducible. You can see it's factorizable. Or you can just say that if x is 0, then 0 is a factor. Okay, so just trying possibilities, because what I said, that there's no formula for coming up with this polynomial, just trying and finding out which polynomial is irreducible mod 3. Let's try x squared plus x plus 1 and see what we get. Oh, this one is reducible. This one is reducible. I'm saying that because if you put x to be 1, if you put x to be 1, then you're seeing 1 plus 1 plus 1, which is 0. That means it can be factorized. That means this can be factorized mod 3. So you can never consider that. What about x squared plus x plus 2? Let's see. Let's try 0. Let me try 0, get 2. Try 1. This will be 1 plus 1, which is 2. Then plus 2, which is 1. Try 2. Try 2. This will be 4 plus 2, then plus 2. What is this? This is 8, which is 2. So again, this is a very good polynomial here. You can not this one, this one. This one. It's a very good polynomial. It's irreducible. You can also use it. You can also use it. So we are only using irreducible polynomials. So you check whether it's reducible or irreducible. And if you find it's irreducible, then you can use it. So in my example, I used this first one. I used x squared plus 1. But I've said you can use any, and of course, the results will be the same. The results will be the same. Because it's only at one point where, at the points where you're finding x squared and you want to replace it with an element of the extension. And I'll show you that the results will just be the same. So we had found that you could also have used x squared, we had found this plus, was it x and then plus 2? Yes, because when x is 0, when x is 1, this becomes 4. And when x is 2, this becomes 4 plus 4, which is, so you can use any of this and many others which are irreducible. Let's go straight to multiplication and see what that are giving us the same results. Now, so I'm multiplying 1. I just want to multiply 0 with the end of the elements. I just getting 0. Let's multiply 1. By this is 1. By that is 2. By this is, so 1 by any element, you just get the element. Just get the element. Okay, let's now come to 2. 2 by 0 will be 0. 2 by that will be 2. 2 by this will be 4. And you are doing it mod 3. So 4 mod 3 is 1. Just dividing by 3 and writing the remainder. Okay. 2 times alpha will be 2 alpha. 2 times this will be 2 plus 2 alpha. All these are elements of this set. 2 times this will be 4 plus 2 alpha. But 4 mod 3 is 1. Then 2 times this will be 4 alpha, which is, what is that? Which is alpha. Okay, let's go to cases where we will require the polynomial. You can see the rest are just the same. Let's go to cases where the polynomial is required. Let me multiply by alpha. This gives me 0. This gives me alpha. This gives me 2 alpha. Alpha times this gives me alpha square. It gives me alpha square. And we've chosen this polynomial. Let's use that. So when alpha is a root to this, we expect that alpha square plus 1 will be giving us 0. So that means alpha square, therefore, is negative 1. But negative 1 mod 3 is 2. That's what we write here. Okay. What about if you had to use this? If you had to use this, then alpha square plus alpha plus 2 will give you 0. So what then is alpha square? Alpha square, therefore, is negative 1 negative alpha, negative 2. Negative alpha, negative 2, which then becomes, does this become? Mod 3, this becomes 2, 2 alpha. 2 alpha plus 1. So this element can be this, if you're using this polynomial. What is that? Oh, is this element, If you're using this polynomial, it will be 2. If you're using this other polynomial, to be this. So it means it will interchange with this other. So when you go here, when you go to this other one, when you're using this polynomial, then you expect this one to be a 2. No, it's not this one. It's 2 alpha plus 1. It's 2 alpha plus 1. 2 alpha plus 1. It will exchange with this one. Exchange with that one. So it will just be the same. The table will have all the elements of this set. So that's what we've seen. We've seen that this times this. If you're using the first one, this one becomes 2. But if you're using the second one, you get this. So let's go to the one that is affected. Let's just multiply this and that and see what we get. So when you multiply this by this, what do we get? Let me see if we get what we just said. This will be 2 alpha plus 2 alpha square. This will be 2 alpha plus 2 alpha square. So the only problem is here. The only problem is here. So when you're using the first polynomial, this becomes 2 alpha plus 2. Instead of alpha square, we have a 2. And so what this becomes is therefore 2 alpha plus 1, which we have. What about if you're using the second polynomial? Using the second polynomial, this will be 2 alpha plus 2 alpha square, but this is 2 alpha plus 1. So when you multiply, then you get 2 alpha. This is 4 alpha mod 3, which is alpha plus 2. And so this is 0 plus 2. So then this one becomes 2. So they just interchange. If you're using this other polynomial. So where there's 2, but now the table just remains the same, the rest of the elements. It's only those other elements that will interchange. Any question? On how to multiply or add? So what I'm emphasizing on is that the polynomial is just you coming up with the polynomial, and there is no formula. You only need to know the conditions, what will be the degree of that polynomial, and that polynomial must be irreducible. Otherwise, there is no other formula that it must be this specific polynomial. No. You have seen now we've used 2 polynomials and we've gotten the same result, only that there are elements that will interchange depending on the polynomial. And then at every row, I think it will be just 2 elements, or maybe 2 or 3. Let's see, like, yeah, everywhere there's alpha square, there'll be that variation. For instance, in this case, you have alpha plus alpha square. Again, so there'll be that variation here. You can see a chart. I think there's a question or something. Yeah, you can use even polynomials with the coefficients. But you have to verify that that polynomial is irreducible. Yes, I know what you mean. What you mean is, for instance, I use a polynomial f of x and I used x squared plus 1. So you may want to maybe change the coefficient. The coefficient here is 1, but you may want to have maybe 2x squared plus 1. So you must check whether it's like this one is reducible. This one can be factorized. This one can be factorized because you can see that when f is 1, then you have 2 plus 1, which is 0. So this one can be factorized. But you can come up with a polynomial that is has coefficients. But before you use it, you confirm that this polynomial is irreducible. Yeah, that's what the person is asking. What about this? F of x, what about 2x squared plus x plus 1? What about that? This would be 3. This one could be irreducible. Let's just see. When x is 0, then you have 1. When x is 1, what do you get? When x is 1, this will be 2 plus 1, which is 3, then plus 1. And then when x is 2, this would be 8. Okay, this would be 8, is it? 8 plus 2 plus 1 is 11, which is 2. So this polynomial here is irreducible. So I think now the question is asking, the one who is asking, the question is, how do you use this to multiply? Let's just go back here and I show you how to use it. Let's go back here. We had multiplied x alpha and alpha. So let's just multiply alpha and alpha. So when you multiply alpha and alpha, what we got, and these are different polynomials, so we expect a different result, of course. But it gave us alpha square. So you just make alpha square the subject. So what we have here is that 2 alpha square plus alpha plus 1 should be 0. So we make alpha square the subject of this formula. So how do we make it the subject of the formula? I just take the rest to the right-hand side. So when you take them to the right-hand side, you have 2 alpha square equals to negative alpha negative 1. In other words, 2 alpha square is alpha plus 2. I've just done this mod 3. Just done this mod 3. You add 3 here, get, oh, this is supposed to be 2. It's supposed to be 2 alpha. I'm doing it mod 3. I'm doing it mod 3. So we are doing it mod 3. Just adding 2 or adding 3 to negative 1. When you add 3 to negative 1, you get a positive 2. And when you add 3 to negative 1, you get a positive 2. But now what we want to make the subject of the formula is alpha square. And you see here, we use our knowledge of the universe, multiply by the inverse of 2 mod 3 on both sides of the equation. So the inverse of 2 mod 3 is 2, because 2 times 2 is 1 mod 3. 2 times 2 is 1. So you multiply by 2 all through. So you multiply by 2 here. Multiply by the inverse. Multiply by the inverse of 2. Because we know that if what we will do here is multiply the inverse on both sides. Multiply the inverse on both sides. But what is the inverse? It's not a half. Just using a half to show that that's what we will do in normal cases. But now in this case, we don't do that. We know that the inverse of 2 is not a half, but it is 2. The inverse of 2 is 2. So multiply by 2 on both sides. So this gives you alpha square. What about this? Gives you alpha, and this gives you 1. Because it will be 2 alpha. 2 alpha mod 3. No, not 2, 4. 4 alpha. 4 alpha mod 3 will be alpha. And then 4 mod 3 will be 1. So this is then what you get. This is what you get. And so when you get this, you just come here and write it there. So instead of this case, our alpha square is alpha plus 1. So here is alpha plus 1. Alpha plus 1. So it means this will be 2. This will be 2. This one will be 2. Let us see. Let us see. So it will be alpha times this. So when you multiply, you get alpha plus 2 alpha square. What is that? I got alpha plus 2 alpha square. When I multiply this one by alpha, I got alpha plus 2 alpha square. So when you get to alpha square, you have options. You can even use this. You can even use this part, because this part is 2 alpha square. Or if you want, you can use this part. There's no problem. Where there's alpha square, you can write this. So what we have then is alpha plus 2 into alpha plus 1. So this is alpha plus 2 alpha plus 1. What is that? Plus 2, not 1. Plus 2. This is 0 plus 2, which is 2. As I say that this part will then be 2. They just interchange. Just interchange. So that is how you do it. If you want to use a polynomial that has coefficients, then and you want to make alpha the subject of the formula, then you realize that you're multiplying on both sides by the inverse of the coefficient. By the inverse of that coefficient. Another question? Because the only thing that is left now is for us to identify the inverse of each of these elements, because what we are saying is that the extension is also a field. So what is identity under multiplication? What is the inverse of what? And so on. And you've seen that commutativity is working. Commutativity you've seen is working. Commutativity is working because you expect that if you have 2 plus alpha multiplied by, let me say, 1 plus 2 alpha, expect the result to be the same as 1 plus 2 alpha multiplied by 2 plus alpha. Expect the result to be the same. This is what we mean by commutativity. That's what we mean by commutativity, that A times B will be the same as B times A. That's what we mean by commutativity. And you can see 2 plus alpha multiplied by 1 plus alpha, 1 plus 2 alpha, gave us 2 alpha. And also, 1 plus 2 alpha, 1 plus 2 alpha multiplied by 2 plus alpha gave us 2 alpha. Commutativity is working. You try any of these elements and you find that they're commutative. Now, what is the inverse of 2 plus alpha? Under multiplication, we've already said that the inverse of A is B if their product is 1. The inverse of A is B if the product is 1. So you can see the inverse of 1, therefore, is 1, because their product is the identity of 1. The only element that lacks the inverse is 0. The inverse of 2, you can see, is 2. The inverse of 1 plus alpha, you can see, is what? 2 plus alpha. You can see is 2 plus alpha. The inverse of 2 alpha, you can see, is alpha, because their product gives you the identity elements. So that's what I wanted to show you today. Just want to show you how to create an extension. You must know what an extension is, that you're given a field, and out of this field, you're coming up with a larger field whose elements are polynomials. Coming up with a larger field whose elements are polynomials of the form A plus B alpha. And then you must know that this extension, the degree of this extension, is the same as the degree of the polynomial you're using. So if the polynomial was of degree 2, then if your base field was 2, and the polynomial you're using is 2, so this becomes the extension, the field extension, and its degree will also be 2. But how many elements does it have? 4 elements. We have 4 elements. So if you're talking of F5, and you are using a polynomial of degree 3, then you expect that this has 125 elements. It has 125 elements. Good. So that's what I wanted you to look at. This is just another example. No, that's another example. So at your own time, you look at it. This one, you know what we are doing here, the same thing. Our polynomial will be of degree 3. So we're expecting to have 27 elements. And those are the 27 elements I have here. So at your own time, you go through it and see, here are these 27 elements. Thank you.